This is the 10th lecture of the mathematical modeling. During this lecture, we're going to learn about higher order linear equations. So we'll look at the general solution of a linear system, and then we'll also look at the complementary and particular solutions of such system. Okay, so during the class, we looked at how the nth order linear differential equation looks like. So it will be in this form. Some function p naught of x times y of n mean the nth derivative of y with respect to x. Okay, and then we'll have yn minus 1 all the way up to y1 derivative and y term. So we'll have ODE in this format with some coefficient functions pi which are continuous on the interval I which we wish to solve this ODE, and they don't need to be linear. Yet this yn minus 1 and y prime y, they are linear terms. Again, when we divide by the coefficient p naught of x, the entire ODE, we can make the coefficient of the nth derivative term into 1, and then it will be in this form. And if the right hand side is equals to 0, we call it as the homogeneous equation, and this is a homogeneous linear equation of the nth order. Now, the principle of superposition of the homogeneous equation says that if y1, y2, y3 all the way up to yn are solutions of this linear homogeneous equation, then any linear combination of those solutions are also a solution of this ODE. So that's what we discussed during the class, and let's look at this example now. Here we have a third order linear equation with constant coefficients, and we want to show that these are solutions of it on the entire R. So we want to find the general solutions. In order to find the general solutions, first of all, let's show them that these three functions are solutions of it. So if y1 is e to the minus 3x, then we know that its first derivative is minus 3 times e to the minus 3x, and its second derivative, this is y1 of second derivative is 9 e to the minus 3x, and its third derivative is minus 27 e to the minus 3x. And if we plug those into the ODE, which is y1 of 3 plus 3 times y1 of double prime plus 4 times y1 of prime, this is number 4, plus 12 times y, that will be minus 27 e to the minus 3x plus 3 times 9, which is 27 e to the minus 3x. The next term, 4 times minus 3, which is a minus 12 e to the minus 3x. The last term is plus 12 times y. Y is e to the minus 3x. So we can see that these two terms cancel out and these two terms cancel out and equals to 0. Therefore, y1 is a solution. I'll show the cosine 2x is also a solution. One can also show the sine 2x. I'm not going to do that. Okay, so look at y2, which is cosine of 2x. we need to find its first derivative, which is minus 2 sine 2x, and its derivative, which is the second derivative of y2, that is minus 4 cosine 2x, and the third derivative of y2 is, or let me write it y2 with 3 this way, that is 8 sine 2x. 8 sine 2x. Now let's apply them to the left hand side of our ODE. So let's compute y3 plus 3 times y double prime plus 4 times y prime plus 12y. So that will be y. The third derivative is 8 sine of 2x plus 3 times the second derivative, 3 times minus 4 cosine 2x, and then the third term is 4 times minus 2 sine 2x, and the last term is 12 times cosine 2x. Can see that here we get minus 12 times cosine 2x plus 12 times cosine 2x get cancelled. Here we have 8 sine 2x. Here we get minus 8 sine 2x. So that is a 0. Therefore, y2 is also a solution. One can show the y3 is also a solution. I'm not going to do that. And so now we can write down, let me say y3 is also a solution. Therefore, the general solution is any linear combination of those three. So let me call it as y of x. That is, let's say, c1 times e to the minus 3x plus c2 times cosine 2x and plus c3 times sine 2x. So that is the general solution. And one can also show that these three functions are linearly independent. We'll do that later on. Okay, here we go. Now, again, we can talk about the existence of the solution and its uniqueness with this theorem. The theorem says that suppose that the function p1, p2, all the way up to pn, so these functions are, and f, also the f, are continuous on the open interval I containing the point x equal a, then given n numbers b0, b1, all the way up to bn minus 1. These are these b values. The nth order linear equation, which is this, it has a unique solution on the entire interval that satisfies the n initial conditions. Okay, so whenever we have an nth order linear ODE with n initial conditions, then it does have a solution, and that solution is unique. That's what this theorem says. Okay, so here we now solve this ODE, which we found the general solution. We found the general solution of this ODE, and we'll be able to find its unique solution given these three initial conditions. Because the theorem before says that any given ODE with that number of initial conditions. So this is the third order ODE. We have three different initial conditions. So this system should have a unique solution. So let's start with the general solution. So we know the general solution of this equation is y of x equal c1 e to the minus 3x plus c2 cosine 2x plus c3 sine 2x. Now, to apply these initial conditions, we need its first and second derivatives as well. So let's find them out. Let me call this one y prime of x, which is the first derivative of this equation. That is minus 3c1 e to the minus 3x. The second term will get so minus sign, so minus 2c2 sine of 2x. The third term is 2c3 cosine of 2x. That's the first derivative. Let's find out the second derivative as well. That would be 9c1 e to the minus 3x minus 4c2 cosine 2x minus 4c4 we don't have c4 c3 sine 2x. Let's call that, this, the second one is 2, the third one is 3. And I'm going to apply these three initial conditions using 1, 2, and 3. So y 0 equals 0. Using 1, we can say 0 equals when x equals 0. So when x equals 0, e to the 0 plus c2 cosine of 0 plus c3 sine of 0. Now sine of 0 is 0, cosine of 0 is 1. We get one equation as 0 equal c1 plus c2. And then if we apply y prime of 0 equal 5 using the second equation we have, we can say 5 equals 2, 9c1 e to the 0 is 1 minus 4c2 cosine 0 is 1, sine 0 is 0. So we'll get this equation. And if you use the third one, the third initial condition, that's the y double prime of 0 is minus 39. We're going to use the third equation to get this. You can say minus 39 equals 2. I think I did a mistake in the second one, so this is wrong. I should have used the second one. So 5 equals 2 minus 3c1. The sine term becomes 0, cosine term is plus 2c3. Okay, the third one, minus 39 equals to 9c1, because e to the 0 is 1, the cosine term is minus 4c2, the sine term is 0. Okay, now we get these three equations. Let me call them 4, 5, and 6. By solving 4, 5, and 6, we can find out the values of C1, C2, C3. I'm going to skip that and write down the values of C1, C2, C3, C4. For example, if we use the fourth one, we can say C1 is minus C2, and then apply this to the let me say to the sixth one. We will get a value of C1 as minus 3, and then if C1 is minus 3, C2 is plus 3, and then if we use the fifth one, we should be able to get the C3. We get value of C3 as minus 2. So the solution, the particular solution of this initial value problem is y of x equals to 3 e to the minus 3x plus 3. Get thing. So this should be minus 100. So it's minus 3. 3 cosine of 2x minus 2 sine of 2x. So this is the particular solution for this given initial conditions. Okay. Now, again, if we know linearly independent solutions of a given nth order ODE, homogeneous ODE, then we can write down the general solution. So, an nth order linear homogeneous equation, which is in this form, can have at most n linearly independent solutions in a given interval. So the great question is how to identify whether the n functions that we have are linearly independent or not. Again, we can use a very similar approach as in the second order linear equation case where we're going to use the Wronskian. Okay, so we're going to use, so before that, so we'll come back to that later on. Now, let's look at what's the meaning of linearly dependent or linearly independent of n different functions are. Here's the definition. Let's say we have n functions, f1, f2, f3, likewise, all the way up to fn. We say they are linearly dependent on the interval I if there exists some constants c1, c2, cn, not all zeros, such that the linear combination of these f with these c's are equal to 0. Okay, so if all the c1s are non-zero, then we can say that there is a linear combination of these functions are equal to 0, mean they are linearly dependent. Otherwise, we call they are linearly independent. Now, let's find out how to identify whether given functions are linearly dependent or not using the Wronskian. Again, suppose we have f1, f2, all the way up to fn are each n minus 1 times differentiable. So they need to be n minus 1 times differentiable because to find out the Wronskian, we need the derivative up to n minus 1. Then our Wronskian will be in this format. It's the determinant of the matrix whose first row is f1, f2, f3, all the way up to fn. The second row is the first derivative of them in the same order. Then the third derivative, fourth derivative, all the way up to the last row is the n minus 1th derivative of these functions in the same order. Once we write it down this way and find out its determinant, then if the determinant equals to 0, then we call these functions are linearly dependent, otherwise they are linearly independent. Okay. Now, again we can write down this theorem. Suppose now we have y1, y2, yn are solutions of the homogeneous nth order ODE. So here we have about the linearly independent solutions. Suppose yn, y2, y1, y2, yn yn are solutions of the homogeneous nth order ODE, this ODE, on an open interval I, where each of these coefficient functions are continuous. Then we calculate the Wronskian, which is W of y1, y2, yn, as we discussed in the previous slide. Then we say if these y1, y2, yn are linearly dependent on this interval I, our Wronskian will be 0. If they are linearly independent, then the Wronskian will be not equal to 0 for every x in the interval I that we wish to solve the ODE, or this open interval that we are talking about. That means we can use the Wronskian to determine whether the given solutions in an open interval are linearly dependent or not. Okay. Now again, in the example 80, and previously we showed that this y1, y2 and y3 are the solutions of this ODE, and also we found out a particular solution for a given initial value problem. Now we want to show that these three solutions are actually linearly independent. Okay, let's do this. So for that we need to find out our Wronskian W. So that's the determinant of y1, y2, y3 in the first row. The second row is y prime, y2 prime, y3 prime. And the third row is y1 double prime, y2 double prime, and y3 double prime. Okay, so the determinant of this matrix. Let's write it for these three given functions. So they are e to the minus 3x, its first derivative is minus 3 e to the minus 3x, and the second derivative is 9 e to the minus 3x. Now the second column we have cosine 2x, its derivative is minus 2 sine 2x, its derivative is minus 4 cosine 2x. The third column start with sine 2x, its derivative is 2 cosine 2x, and its derivative is minus 4 sine 2x. You need to find out this determinant, and I know you know how to find out the derivatives. That is quite a long process. We need to follow through through an desired row or a column. Let me consider the first row, and I can say e to the minus 3x times the determinant of minus 2 sine 2x, 2 cosine 2x, minus 4 cosine 2x, minus 4 sine 2x. And then the second term with the minus sign, so minus cosine 2x with the determinant of minus 3 e to the minus 3x and 2 cosine 2x, 9 e to the minus 3x, and we have a third term with the plus sign and sine 2x with the determinant of this simple matrix, which is 3 e to the minus 3x minus 2 sine 2x. Okay. Now, all we need to do is we need to expand all these determinants and simplify it. If I do it, e to the minus 3x, we get 8 sine 2x squared plus 4 times 2 is again 8 cosine squared of 2x. Then we get minus cosine 2x times 12 e to the minus 3x sine 2x minus 18 e to the minus 3x cosine 2x. And then from the last one we get sine 2x times 12 e to the minus 3x cosine 2x plus 18 e to the minus 3x sine 3x. Okay. Now, this term, when we expand with the cosine 2x, get cancelled out with this term and this term with the minus 18. Hold on. This is 2x actually. Okay, so these two terms get cancelled out and we'll have e to the minus 3x is common. We have 8 times sine squared 2x and then we get another 18 times sine squared 2x, which is 8 times 18. 8 plus 18 is 26 sine squared 2x. And similarly, we get 8 cosine squared 2x plus 18 cosine squared 2x, which is 26 cosine squared of 2x. And we know that sine squared plus cosine squared equals to 1, or we get 26 e to the minus 3x, which is not equal to 0. Therefore, y1, y2, y3 are linearly independent. This means linearly independent. I wrote it in short. Okay. Now we can get an idea about the general solution of the homogeneous equations of the nth order. So for that we can use this theorem. The theorem says that let y1, y2, yn be linearly independent solutions of the homogeneous equation on an open interval I, where these coefficient functions are continuous in this interval I. If y of x is any solution of the differential equation on this interval I, then there exist constances c1, c2, cn, such that y is a linear combination of these y1, y2, yn with these coefficients c1 to cn. So in other words, the general solution of an nth order ODE is a linear combination of n linearly independent solutions. Okay. Now, how do we find the solution of non-homogeneous equations? Okay, suppose we have an nth order non-homogeneous equation where our right hand side function is f of x and I label it as the second equation. And suppose that this equation has a solution yp. We call it as the particular solution. So it's a particular solution of this non-homogeneous equation. And y any other solution, let's say y is any other solution of it, then if we look at y, c, which is y minus yp, then we can show that this is a solution of the associated homogeneous equation. How we can do that? Because if you plug this into this, then we'll get yn, and then separate the variable into y and yp and subtract them, then we have the right hand side equals to 0. So for example, if yc is a solution of 2, then uh, y, if we apply y, we'll get f of x in the right hand side, and then again for the yp we'll get f of x, and then f of x subtracts f of f, we'll get our right hand side equals to 0. So okay, so I'm actually not going to do this part, but you can try doing this. If y and yp are solutions of this non-homogeneous equation, then if we look at the combination y minus yp, then we can show that this yc is a solution of the homogeneous equation with the right hand side 0. And therefore, we can rewrite this taking y by isolating y. So y then will be yc plus yp. Now, so this will be the form of general solution of the non-homogeneous equation 2, where yc is the general solution of the homogeneous equation. And we know yc, we call it as the complementary solution. Yp is the particular solution. And yc, the complementary solution, we can write down as a linear combination of n linearly independent solutions of the homogeneous equations, where y1, y2, yn are linearly independent solutions of the equation 3, the homogeneous equation. So we know all the solutions of the homogeneous equation and a particular solution of the non-homogeneous equation, then the general solution will be the superposition of those two. That's what this slide says us. Okay, so that's also the theorem here. Let yp be a particular solution of the non-homogeneous equation. There's on an interval I, where pi and fi are continuous on that interval, and also let y1, y2 all the way up to yn be linearly independent solutions of the associated homogeneous equation, which is this. Then the general solution of this non-homogeneous equation, equation 2, is a linear combination of the linearly independent homogeneous solutions of the homogeneous equations, which is this part, plus this is also called as yc, the complementary solution, plus the particular solution of the non-homogeneous equation. Okay, so with that information, let's try to solve this example 81. We have the second order linear equation with 12x in the right hand side as the function with these two initial conditions. We want to find out we need to solve this equation. Okay, here I have given some hint as well. Cosine 2x and sine 2x are solutions of the homogeneous equation, and yp equal 3x is the particular solution. Okay, so let me show this statement is correct. So if yp is 3x, then its first derivative is 3 and its second derivative is 0. Yp is second derivative. And if we plug this into our left hand side, which is y double prime plus 4y double prime of p plus 4 times yp will be 0 plus 4 times 3x, which is 12x. So that's the right hand side. So that means yp is a solution of the non-homogeneous equation. Sorry. Of our non-homogeneous equation. So the yp is the particular solution. And also, let's show that cosine 2x and sine 2x are solutions of the homogeneous equation. Okay, so let me call it as y. Let me call y1 as the cosine 2x. Then its first derivative is minus 2 sine 2x. And its second derivative is minus 2 cosine 2x. And if you look at y1 double prime plus 4 times y1 will be minus 2 cosine 2x plus 4 times, this is times 2. This is actually minus 4 times cosine 2x plus 4 times cosine 2x. That's equals to 0. That means y1 is a solution of the homogeneous equation. Similarly, we can show that y2, which is sine 2x. If y2 is sine 2x, its first derivative is 2 times cosine 2x, and its second derivative is minus 4 times sine 2x. Thus, we can see that y2 double prime minus 4 times y2 equals to 0. Therefore, we can say y1 and y2 are solutions of the homogeneous equation, which is y double prime plus 4y equals 0. Now, with these informations, we can write down the general solution of the given ODE. The general solution will be y of x equals to linear combination of the y1 and y2, which is c1 times y1 plus c2 times y2 plus the particular solution. We do not put a linear combination with yp. We just add yp. Okay. And if I rewrite with y1, y2, and yp, it will be c1 times cosine 2x plus c2 times sine 2x plus yp is 3x. So this is the general solution. And using these two initial conditions, we will be able to find out the unique solution. So we found out the general solution as c1 cosine 2x plus c2 sine 2x plus 3x. It's 3x. Yeah. And to apply the initial conditions, we need to look at its first and second derivatives. The first derivative is minus 2c1 sine 2x plus 2c2 cosine 2x plus 3. And the second derivative is minus 4c1 cosine 2x plus 4, no, not plus, minus 4c2 sine 2x plus, no, nothing. Okay, now let's apply the initial conditions. We have two initial conditions. Oh, actually, I didn't. I don't need this. I don't need this. I don't need this. Okay, so let's apply y of 0 equals 5 using the first one. And then 5 should equals to c1 times cosine 0 plus c2 times sine 0 plus 3 times 0, which means 5 equals to c1. If we apply the second initial condition, y prime of 0 equals to 7, we get 7 equals, we're going to use the second equation for that, 7 equal minus 2c1 sine 0 plus 2c2 cosine 0 plus 3 gives us 7 equals minus 2c1. Oh, no, I don't get this term. 7 equal 2c2 plus 3. From there, we can see c2 should be 4 divided by 2, which is 2. Therefore, our solution is 5 cosine 2x plus 2 sine 2x plus 3x. Yes. Yeah, that's it.